computing? Thanks.
Yep, absolutely. Thank you so much. My name is Kevin Owen, and it's a pleasure to me to present to all of you the Professor Oliver, Professor of Electrical Engineering and Computer Science, and Professor of Physics at Massachusetts Institute of Technology, Director of the MIT Center for Quantum Engineering, and Associate Director of the MIT Research Laboratory of Electronics. Professor Oliver, the floor is yours.
Great, thanks so much, Kevin, and sorry to interrupt the end there to the Amazon folks. I didn't realize that they were still doing their presentation, but it's really a pleasure to be here. Let me share my screen and then we can get started. And let me just quickly ask, are you seeing the correct version, or do I need to change the display settings?
Looks great.
Looks good? Okay, fantastic. So I'd like to talk today about engineering quantum systems of superconducting qubits. And I'm Will Oliver at the Massachusetts Institute of Technology. Really pleased to be here. And thanks again for the invitation. Let me get a pointer. Awesome. Yeah, so this is a general introduction. I realize you're kind of late in the hackathon, but I'd like to give a general introduction to quantum computing with superconducting qubits. Before we do that, I think it's worthwhile to go back and take a look at the history of classical electronic computing. So, the vacuum tube was invented in 1906, and it was used for radio transceivers for many years. And it was a good 40 years before we saw it appear in this computer in this picture called ENIAC. That was 1946. It takes up the whole room. You can think of today's quantum computers probably as something like this. Now, the next year, 1947, was the invention of the transistor at Bell Laboratories. This is a bipolar junction transistor. And within about 10 years, we had a fully transistor-based computer called TX0 or TIXO that was developed here at MIT. Again, you can see it takes up a whole room, basically. And it had transistors, but wasn't used, or they weren't manufactured in the way that we see them today in chips. They were just basically soldered together. To get closer to where we are today, we needed the integrated circuit, shown here in the late 50s. But it was still, you'd have to wait until the 70s to get chips like the one I show here, which is the Intel 4004, a 4-bit processor with 2,000 transistors. And it would be another 20-25 years to get to the Pentium Pro with millions of transistors, and then another 20-25 years to get to where we are today with billions of transistors on a chip, multiple cores, and graphical processing units. So from our standpoint today, with these fantastic classical computers that we've got, it's well over 100 years of development from the first fundamental element. We can compare with that quantum computing, which is far more recent or nascent. In the early 80s, people like Richard Feynman and Uli Mannin and others said, look, it's hard to simulate quantum systems using a classical conventional computer. Why don't we do that instead with another quantum system? Okay, basically proposing a quantum computer. But how to do that, it would take 15 years before we started to see the first algorithms that we think of when we think of quantum computing today. So Shor's algorithm, for example, for cryptanalysis, adiabatic quantum computing, quantum annealing from Nishimori and Eddie Farhi, Grover's algorithm. Of course, along the way, error correction. And in the early 2000s, Ike Chuang and colleagues at IBM demonstrated that they could factor 15 into 3 times 5 experimentally on a very small quantum computer, but showed that Shor's algorithm, this factoring algorithm, can work. But it's another 20 years to get to where we are today, which is we've got small scale computers in the cloud, quantum computers with between 10 and 100 qubits or so. And you can access them, and you are accessing them, right, through your hackathon. So the takeaway message, though, is that Well, one, quantum computing is real. We know that. And it's transitioning from a laboratory or a scientific curiosity to a technical reality. That's happening around us right now. But we know that advancing from fundamental discovery to useful machines, it's going to take time. It's going to take engineering. And maybe another takeaway is that you must be in the game to play. And what I mean is that the companies who are building these types of very, very complicated chips today, they were in the field for decades. And so, hats off to all of you for, getting in and starting to play with these new small machines and developing algorithms that we can run on them, even though the hardware is still at a very early stage. So with that, let me present the outline. I'd like to talk a bit about, just an introduction to quantum computing, maybe a different way to think about it, and superconducting qubits. Then I'll talk about engineering quantum systems. What do we need to do next? And as part of that, if we have time at the end, I'll talk a little bit about some 3D integration work that we're doing here at MIT and Lincoln Lab. So first off, I guess you guys know this, but how is a quantum computer different? And I like to compare it to classical bits, transistor. There's a voltage, there's no voltage. Those bits have states, 0 or 1, and they're discrete. And transistors almost never have an error. Error rate's better than 1 part in 10 to the 20th power, right? So if something goes wrong here, knock on wood, but if something goes wrong, it's probably a software error. It's not that one of our transistors failed. The measurements as a result are deterministic, that if we set it as 1, we'll measure as 1. And if we set it as 0, we measure as 0. Quantum computers, of course, are different. They're based on quantum bits. And really, any coherent 2-level system will work. And there are many technologies. We'll look at that in a moment. But you can think of it on the block sphere, or the planet Earth, where the North Pole is 0 and the South Pole is state 1. And if you're at the North or South Pole, you're basically one of these classical bits. Of course, a qubit can be a classical bit. But when you're anywhere other than the North or South Pole, you're not a classical bit anymore. You're in a superposition of both 0 and 1 with some weighting coefficients called probability amplitudes. And the thing that is important to remember is that that's a quantum mechanical state, but it is a single state. It is a state that carries aspects of 0 and 1 simultaneously. It's not a classical superposition that has both at the same time, but they're distinguishable. This is a single quantum state that carries aspects of both 0 and 1 simultaneously. And they're called, of course, superposition states. Now, if you're on the equator, for example, then the probability amplitudes, their magnitude is equal. It's 50-50. And as a result, the measurement, of course, being probabilistic, would say that 50% of the time when you make a measurement, you snap back to the North Pole, and 50% of the time you snap back to the South Pole. And even if you go to the same place on the equator and make a measurement again and again, randomly, 50-50, flip a coin, one of the purest random processes we know of, you will 50-50 go to the North or South Pole. And so quantum computers, rely on encoding information on these fundamentally different, qubits. And the consequence is that if you want to, build a computer out of this, one consequence is the following, which is that if you have, let's again look at a classical computer. If you have n bits, you do have an exponentially large state space, 2 to the n. But you can only represent one of those states at a time. So for example, if n equals 3, then 2 to the 3rd power is 8. And you can represent 0, 0, 0, or you can represent 0, 0, 1, et cetera, all the way up to 1, 1, 1. But again, even though there's an exponentially large number of those combinations, you can only represent one of them at a time. And so if you want to do computation, say with all of those states as inputs, you really only have 2 choices. One is that you can take a single classical computer and you feed the input in one at a time, and you get some function of that input as an output, but you have to do it serially one at a time. And the alternative is you could buy many copies of the hardware, so many computers, and do it in parallel. But either way, if you have an exponentially large number of states that you want to run through, you either need exponential time or exponential hardware. So quantum computers, of course, are different. If you have n qubits, you again have this 2 to the n state space. But the difference is that you can put all of those states or aspects now into a single quantum superposition state, each with their own unique coefficient in front. And this leads to a quantum version of parallelism and also quantum interference. And these two together are what underlie the power of quantum computation. Now, figuratively, you can think of it as having a massive superposition state that you feed into your quantum computer. It operates on that, and you'll get a massive superposition state, quote, out. But we'll see in a moment that measurement will collapse this down to a single state. Now, I want to emphasize that it's important to realize that we're not calculating every single function here, input to output. What's happening is through parallelism and interference, the state that encodes the right answer is quantum mechanically enhanced through constructive interference, while the wrong answers, so to speak, are suppressed through destructive interference, such that at the end of the day, only one of these aspects carries near unit probability. Okay, so how do we take advantage of this quantum information? Well, in a classical Boolean logic computer, we use Boolean logic gates, such as the NOT gate or the AND gate, the OR gate, etc. And the truth tables are here. I won't run through them all. But the point is you don't need all of them, just a small set. So for example, the NOT gate plus the AND gate is universal. And it's also not unique. There are many other combinations. And a universal set of gates means that with this choice of gates, you could start at any state in the state space and you can go to any other state in the state space, which means you can run any arbitrary Boolean logic algorithm. Now, some choices may be more efficient than others for certain problems, that's fine. But the point is that some small set of these gates together can be universal and it's not unique. Quantum is no different. Well, it is different, of course. It uses quantum gates, but otherwise, conceptually, it's no different. We have quantum gates, such as the X gate, the Y gate, the Z gate, etc. And these represent different types of rotations around the qubit. These are single qubit gates. I show here the matrix representation and also the truth table. We also have 2 qubit gates or entangling gates, where the action on one qubit depends on the state of another qubit, right? And again, the truth table and the matrix representations are here, also CZ gate. But the point is that with just a handful, you don't need all of them, with just a handful of these gates, you can form a universal set of quantum logic gates, which means you can perform any arbitrary quantum logic. Again, it's not unique. There are other choices you could make. And it's one point to make is that often, on a quantum computer, in principle, you could run Boolean logic algorithms, right? But often a quantum computer will do that no better than a classical computer, often much worse, because the clock speed of a quantum computer often is much slower than a classical computer. And actually implementing that Boolean logic may take more steps. So it's not the case that a quantum computer can run efficiently any classical algorithm, but for certain quantum algorithms, quantum computers can vastly outperform. Quantum computers can outperform a classical computer. So let's take a look at some examples of gates. So the classical NOT gate, we know takes a 0 to 1 and a 1 to a 0. It inverts. It's called an inverter. And the quantum version basically does the same thing. We use this notation to indicate quantum states. An example is the X gate, which rotates around the x-axis. And here's an example of that. This block sphere, or the planet Earth that we talked about, the North Pole is 0, the South Pole is 1. And the blue arrow that you see is representing the qubit state. And the red arrow that's coming in and out of this is representing the pulse that we're using to drive this gate. And the pulse is shown on the right as a function of time. And if you just go from the North Pole to the South Pole, basically this is just a classical gate. You go from classical 0 to classical 1. But you could start anywhere on the surface of the planet Earth. And in this case, you're rotating from a starting point that's a superposition. You still rotate 180 degrees to a endpoint that's also a superposition. And what this particular gate does, you can see at the bottom, is it takes the coefficients alpha and beta in front of 0 and 1, and it swaps them. Okay. So this is an example of a single qubit quantum gate. Now, we can also, by analogy, look at a 2-qubit controlled NOT gate. The classical analog we call exclusive or the XOR gate. And it has a control bit and a target bit, call it X and Y. And the truth table is shown here. But one way to look at this truth table is to say that when your control bit is in state 0, the output of this gate will basically follow the Y bit, so 0 and 1. But if the control bit is 1, we're going to flip the Y bit, and that's the output. So 0 becomes 1 and 1 becomes 0. So that's the classical XOR gate. And it's the same for the quantum CNOT gate. Of course, we're using this quantum notation over here, the Dirac notation, but otherwise the truth table is the same. We have a control qubit X, a target qubit Y. This is the symbol for CNOT. And when qubit X is in state 0, the state of qubit Y is passed to the output. But when qubit X is in 1, qubit Y is flipped. Okay. So it means that some operation or rotation that we're doing to qubit Y depends on the state of qubit X. Now, this is very interesting in this example, where we take as our input the control qubit X will be in a superposition of 0 and 1, and the target qubit Y is just in state 0. And the rules of linear algebra apply here, so we can take these one at a time. So when the control bit is in 0, we just pass, the Y bit to the output. So we see that here. But when the control bit is 1, we need to flip that. So 0 becomes 1. And what we see now is that we've created a state which can no longer be factored or separated into something which is only qubit X and only qubit Y. And another name for this is an entangled state. Now, you have to show that this property holds no matter which basis we're looking in, but this is an example of an entangled Bell state, and that's one reason we call this an entangling gate, is because it can create entanglement starting with 2 qubits that are not entangled. Okay, so these are just 2 examples, an example of a single and a 2-qubit gate, but a universal gate model or gate-based quantum computation is achievable with just a small set of these single and 2-qubit gates. So to run an algorithm, and I know that you're developing those here, the way that I intuitively think of it is we start generally with a massive superposition state, equal superposition state, and we pass that into our computer, and we then, according to some prescription called the algorithm, we apply, for example, single qubit gates. And the thing to remember is that we're applying one gate, and we're applying it to only 1 qubit, but we're impacting the coefficients on all 2 to the n coefficients in this single superposition state. So this is followed by quantum interference, and the net result is that all of these coefficients in principle will change. So 1 gate applied to 1 qubit, and we're changing 2 to the n different probability amplitudes. Now, we'll also apply coupled qubit operations, again, where the state of 1 qubit impacts the rotation on the other, followed by quantum interference. And at the end of the algorithm, generally speaking, we would like all of the probability amplitude to reside in front of one, or in some cases a few, but let's say one of these aspects in the superposition state. And that's because we know that measurement is a collapse, right? Ideal quantum measurement is a collapse. And the state that we will measure goes as the magnitude squared of this coefficient or probability amplitude, right? And so if this amplitude is 1, with probability 1, we will measure this as our result. And the results 0, 0, 1 on qubits 1, 2, and 3 encode the answer to whatever problem this algorithm is solving. If this were not the case, if we had distributed probability amplitude across all of these aspects, then randomly, but according to the probabilities of this magnitude squared, we would get different outputs, right? And since there are an exponentially large number of these possible outputs, without this coalescence of the probability amplitude around the right answer, we would just get out what is seemingly random numbers or random results. Okay, so that's great. So why don't we have quantum computers today? Well, or at least large-scale quantum computers. And it comes down to two time scales. One is the coherence time, and that's the qubit's lifetime. So we're pretty good at setting the state of our qubits in a quantum computer at time t equals 0, preparing that state. We'll just call that psi. Let's imagine it's perfect. But instantly from that time forward, psi, the computer is interacting with its local environment. Now, of course, I know the Hamiltonian and I know the gates that I'm applying, and so I can predict the time evolution of psi from this starting point to some later time, but I don't know what's happening here, right? And so as a result, over time, the state psi begins to blur and eventually disappears. Now, the qubits are still there, and they're in some state, but I just don't know what that state is, because my prediction based on the Hamiltonian I know that takes me forward in time, this time evolution, is different than that Hamiltonian plus these environmental disruptions, right? And that's why we effectively lose the state. So that time scale over which that happens is the coherence time. Now, the second time is the gate time. And that's a typical time required for a single gate operation. You might pick the one that takes the longest because that's the most conservative and use that as your metric. And the figure of merit then is the number of gates that we can apply within the coherence time that we have. And that's an intuitive figure of merit. A rigorous metric we would call fidelity. Okay. Now, one point to make here is that long coherence times alone are not sufficient, right? It's this ratio that's important. How many gates can I perform within the coherence time that I have? And, to use a ridiculous example, you could think of a neutrino having a very long coherence time. That's true, but I basically have no way to control it. And so it takes me a very long time, if ever, could be infinite, to do a gate. And so it's not a good qubit. Right? So long coherence times by themselves are not sufficient. It's how many gates can I perform within the coherence time that I've got. And so with that, we can look at different qubit modalities and compare them against one another. And let me just say right out of the box that this is circa 2019, and the performance is now a little bit better, but roughly speaking, this is what it looks like. What we've got on the left here are the number of operations before an error, that figure of merit we just talked about. And that's basically 1-to-1 in the gate fidelity on the right. So if I have one error in 100, that's 99% fidelity. One error in 1,000 would be 99.9% fidelity. And in the horizontal axis, that's the gate speed, so the rate at which I can apply these gates, or 1 over the gate time. And of course, the upper right corner is the best performance. High speed, high fidelity. Now, I have a number of colleagues here at MIT who are working on these modalities. And just to give some names and faces, in the trapped ion space, people like Ike and Rajiv and John Ciavarini at Lincoln Lab are working on the trapped ion modality. My own research, along with my colleagues here at MIT and Lincoln, are working on superconducting qubits. And basically, you can see that, they're both have strengths and weaknesses. And so the trapped ions, in their case, they're trying to make their computers faster, their gates faster, and also trying to achieve higher fidelity 2-qubit gates. For the superconducting qubits, we're already pretty fast, so we're trying to improve the gate fidelity of single and 2-qubit gates. Now, these other modalities that you see here, neutral atoms, definitely exciting, up and coming. We just heard that Quera, a startup company here in Boston, founded by Vladan and colleagues at Harvard, just became available on AWS, Amazon Web Services. So here are some folks working on the neutral atom modality at MIT. NV centers They can be used as qubits. Here are some folks working on that here at MIT and Lincoln Lab, but they really shine as quantum sensors as well. And I also have just started in my own group an effort on silicon quantum dots, which is another modality. So look, there are many candidate technologies that are under development to realize the promise of quantum computing. And I believe in your hackathon, you're using trapped ions from IonQ and superconducting qubits from Rigetti and Oxford and elsewhere. So those are maybe the two leaders today, but you know, if we look at the history of classical electronic computing, you know, we started with vacuum tubes, but they were later supplanted by bipolar junction transistors, TTL logic, ECL logic, eventually CMOS, right? So the technology is going to unfold over time. Oh yeah, and I mentioned that most of these have improved about an order of magnitude since I originally made this slide. They've also got a little bit faster. Okay, so with that, let me move on to superconducting qubits. We often call them artificial atoms by analogy to this periodic table of natural atoms that we have. And somehow this graphic got a little bit screwed up, but natural atoms are defined by protons, neutrons, and electrons. And the numbers of electrons and protons determine which element we have, and the number of neutrons, of course, which you know, can be there can be many, you know, elements can have many numbers of neutrons therein. And similarly with our superconducting qubits, we make them, they're circuits made from inductors, capacitors, and Josephson junctions. And these circuits together, or these elements together, form a circuit, which is basically a resonance circuit. It's a nonlinear resonance circuit. And you know, we can choose the number of junctions or the number of capacitors and thereby design artificial atoms with custom parameters, each with different properties, just like different elements have different numbers of protons and electrons, neutrons, and they have different properties. Okay. So life starts as a resonance circuit. An LC resonance circuit shown here has a resonance frequency. We'll call that omega R. And if you look at the potential profile, the potential energy of a resonance circuit, it's harmonic. That means it's quadratic. And if I cool this down to a low temperature, where low temperature means that the energy scale KT is much less than this energy scale Planck's constant times the resonance frequency, then this is a quantum circuit. It's a quantum object, has discrete energy levels, 0, 1, 2, which count the number of excitations that I can put into the resonator. And interestingly, the current and the voltage are not commuting operators anymore. And so if I measure current perfectly, I don't know the voltage, and vice versa. They have an uncertainty principle. The problem with this is it's not a qubit. And if I try to drive the 0-1 transition uniquely, what I find is I'm also resonant with the 1-2 and the 2-3 and the 3-4, et cetera, which I don't want. And so to get around that, I need to introduce a nonlinear element. And the one that we introduce here is called the Josephson junction. It is a tunnel junction where the leads are superconducting. In this case, it's aluminum, typically. And they're separated by a thin insulating barrier, aluminum oxide. And Brian Josephson won the Nobel Prize in the 70s, I believe, for basically articulating the current and the voltage relation for current or through the junction and voltage across the junction. I'm not going to get into detail on that, but what I want to emphasize is that if I use those to define inductance in the usual way, then the inductance of this Josephson junction is highly nonlinear in the current that is traversing it. And you can then further calculate what the energy potential profile is. And it turns out that it has a cosine dependence rather than a parabolic potential dependence. So we call this an anharmonic potential. So basically, replacing the inductor with a Josephson junction, you still have a resonance circuit, but now it is a nonlinear or anharmonic resonance circuit. The potential is now a cosine. And the consequence of that is that the 0-1 transition frequency is distinct from the 1-2 transition frequency. They're different. So I can effectively draw a box around 0 and 1 and address that uniquely. That's my qubit. Okay, but just like with natural atoms, of course, there are other energy levels, there are other states of that atom, but I'm just going to focus on a subsystem, and we'll call that the computational subspace. Okay. So we cool these down to very low temperatures, and the reason we do that is because we typically choose that 0-1 transition frequency to be 5 gigahertz. Now, that's a choice. We could choose a different frequency, but that's a good frequency because there's a lot of experimental microwave gear that allows us to implement the control along the lines of what we saw before, and I'll show it in just a minute again. So if once I choose 5 gigahertz as my transition frequency, I've set a temperature scale that I need to respect. 5 gigahertz in thermal energy is equivalent to 250 millikelvin. Meaning that if my 5 gigahertz qubit is sitting at 250 millikelvin, just the black body radiation can drive transitions. We don't want that. That's the environment. We want to suppress that. And so the way around it is to go to low temperatures, much lower than that. A factor 10 is enough because this Boltzmann factor is in an exponent. So we operate at around 20 millikelvin, and this is achievable in something called a dilution refrigerator. You see a picture of one of ours here. These are commercially available. 40 years ago, this was somebody's graduate student project, but today you can just buy these. The size is about 0.5 meter in diameter, 0.5 meter depth, and all of this region is at 20 millikelvin. And you can see many microwave elements in here, like filters, microwave switch, isolators, circulators, and you can even see the packages which hold the quantum chips that have the few qubit processors on them. Now, we fabricate these using standard silicon processing tools that you would find in a CMOS foundry. So these are manufactured. It's lithographic scalability. What I'm showing here is a 200 millimeter wafer, silicon wafer, and on here are designs. This is just a design, by the way. But if we zoom in on one of these, this has thousands and thousands of qubits. But if we zoom in on one of these, you can see 5 qubits in a line here. This plus sign that you see is a capacitor. It's a lateral capacitor to ground. In the northeast, I guess, these are readout resonators that we use to read out the qubit. And in the southwest are some control lines that we use to control the qubit. So if we zoom in on one of them, you can see this plus capacitor, this plus sign. That's a capacitor to ground. And you can see the control lines down here, readout up in the northeast. Now, this small loop that you see, we'll zoom in on that next. That's here. This loop is called a squid, and it contains 2 junctions. The reason we make a loop with 2 junctions is that if I put a magnetic field through this loop, I can now tune the 0-1 transition frequency with that magnetic field. So that's a useful thing to do. I can tune my qubit while it's in situ inside that fridge. And then we can zoom in further on one of these Josephson junctions. Here it's shown here, and we're now down at the 100 to 200 nanometer length scale. Okay, good. Now, we control these with microwave gear, and the way that the control is implemented on superconducting qubits is with what's called I-Q mixing. So I means in phase, Q means quadrature. We're going to associate the in phase component with the x-axis and the quadrature component with the y-axis. Now, what's happening here is the LO, the local oscillator, is fed into this mixer, and it's close to the resonance frequency of the qubit. And we multiply, this mixer will multiply with that a pulse with some intermediate frequency from an arbitrary waveform generator. And we'll send that pulse either to the in-phase port or we'll send it to the quadrature port. Now, if we send it to the in-phase port, this pulse comes out, they're multiplied together. The frequency is the sum and difference of them. We'll just keep one of them. And the frequency now is resonant with the qubit. But we note that there's no phase shifts, that's 0 degrees. If we instead choose the quadrature port, the mixer will shift the output by 90 degrees. So we have an in-phase and a quadrature port that we associate now with the x and the y-axis on the block sphere of the planet Earth. So where this simulation is now is that we have a rotation around the y-axis and then a second rotation around the y-axis. And then if it starts over, We're now using the in-phase port. We'll do a minus around -x. We'll switch to y. So now we're going to rotate around the y-axis. And all we're doing is changing between the I port and the Q port to do this. And the amount of rotation is related to the area under this pulse. And so these larger ones are pi pulses. They rotate 180 degrees. These smaller ones were pi over 2. And this is how we can rotate the qubit state around on the Bloch sphere. Last thing I'll say about superconducting qubits is that, we've been developing them as a community for over 20 years. The first qubit was demonstrated in the late 90s by a group at NEC. Had about a nanosecond coherence time. But since then, really through efforts worldwide by researchers looking at materials, fabrication, and design, we've been able to improve the coherence time more than 5 orders of magnitude in that intervening time. And one feature at MIT and at Lincoln Lab is that we don't focus on just one of these types. We look at and exercise many different types. And here are some times that we're currently achieving with these different types or different elements, if you want to think of it that way, of superconducting artificial atom. If you look at the fidelities that we're achieving, this is data from the HAQS group here, my group at campus. The single qubit fidelities that we're able to achieve are greater than 99.9%, or 3 nines as it's written here. So that's better than 1 in 1,000 error rate. And this is done through interleaved randomized benchmarking. The 2 qubit gate fidelities, we've demonstrated I swap with about almost 99.9% fidelity, and a controlled Z gate with about 99.6% fidelity. These are our best numbers so far. And if you'd like to read more about this, you can see this in the paper here. But this is basically where we are here, and I would say there are other groups around the world that can do roughly this level of fidelity as well. These are what the qubit chips look like today. So in the lower left is IBM's Eagle processor with 127 qubits. This is Google's Sycamore processor that had, I believe, 53 qubits. Here's one of Rigetti's processors with 20 qubits. This one's a little bit dated. Here's one of IonQ's quantum computers. You can't really see it, but inside it is the quantum computer. And this is D-Wave. Now, these are gate model, but D-Wave is a different type. It's called a quantum annealer. This, of course, is not a quantum computer. You'll recognize this as the Wright Flyer. It was the first airplane that was self-propelled, had a human on board driving it, controlling it, to achieve flight. This was 1903. And this was heralded as the beginning or the dawn of aviation. When we saw this, we weren't ready all to get on that airplane and fly it, but we knew that within a couple decades, there were going to be commercial airplane companies, not just building airplanes, but planes that we could fly in as consumers, right? And I think this is about the stage where we're at now, right? We've had our Wright Flyer moment. But so there's a lot of promise to quantum computing, but we're still at a very early stage. And to realize the full promise, we need to engineer systems that are robust, reproducible, and extensible. These quantum computers are still very, very small scale compared to what we're going to need for commercial applications. And so I'd like to talk a bit about how we're going to get there. So with that, of course, it requires engineering and an architecture. And so the architectural layers of a quantum information processor basically are shown here on the right. This one's due to Cody Jones. When he was at Stanford, he wrote this paper. At the top is the application. So the interface, the user interface, where you program your quantum computer as you're doing now. At the bottom are the physical qubits. That's the hardware. They're faulty. They have an error rate. And in between are these 3 layers that we're familiar with, of course, from classical computing. So first of all, we need a logical controller that's going to compile what you've written as your algorithm and figure out what gates you need to run that algorithm, given the hardware you've got, and it implements those algorithms. But it also does another thing. It actually has to perform error suppression and error correction, and it does that on every cycle. Now, error suppression is applying gates without feedback. It's just applying gates that we know is a good thing to do because it reduces what turns out to be coherent errors. An example of which is dynamical error suppression or dynamical decoupling. We'll see an example in a moment. And we do this because it's easy to do. It requires low overhead on our part to do it. And it corrects for some of the errors. And that makes these physical qubits as good as we can possibly get them. But of course, it doesn't take care of all errors. And for some errors that we're left with, we need to do active error correction. And that involves detecting that an error occurred, recognizing it, and then figuring out what pulse I need to apply to fix it. And also when I need to fix it. I don't need to fix it necessarily right away, but I got to keep track of it. And then sometimes I may need to go in and fix it. So I like to, illustrate this through a game that you're probably familiar with called lacrosse, where the player carries a stick with a basket at the end, and you try to hold a ball as you run down the field, and then you want to throw the ball in your opponent's goal. And to illustrate physical qubits, I'm going to use this video here, which I'll run in just a moment. But this is not the way you would play lacrosse. This is the wrong way, but it illustrates the point, which is that if you just carry the ball in your stick, like is shown here, and you run, the act of you running has errors. But of course, the ground that you're running on is also bumpy and introduces more errors, as you can see. So as you're running, that ball starts flopping around, and pretty soon it's going to fall right out onto the ground, right? So that is due to the actual running event, right? So that would be like the gates you apply having errors, as well as the fact that the ground or your environment also is introducing fluctuations. So of course, you don't play lacrosse like this. Rather, the way that you play lacrosse is you cradle. And cradling is an example of passive error suppression, because cradling is just something you do. You don't think about it. There's no feedback loop. It's a good thing to cradle, so you do it. You see, by cradling, what's happening is that the ball is decoupled from the player running, and it's also decoupled from any, variation in the ground, bumps in the ground. And as a result, the ball is decoupled from those fluctuations and stays in the basket until he's ready to score this goal. Now, despite the fact that we do all that, we still occasionally will have an error. The defender, the big D, decoherence comes up behind you and may knock the ball out, okay? We don't prevent that with passive error suppression. And when that happens, the first thing we need to do is detect that an error occurred. We recognize that the ball fell out. And then we actively have to go over and pick it back up. Now, you'll notice that when the ball falls out, the player first identifies that it fell out. Okay, I'm going to pick it back up, and then immediately starts doing passive error suppression again, cradling, right? Basically, this is what we need to do in a fault-tolerant quantum computer. And so in the last few minutes, I should say people are working very hard to do that. But in the last few minutes, I'd like to talk about 3D integration. And if we look at the types of circuits we have today, here's a linear chain of 5 qubits in a row. We saw this one earlier. We looked at the fidelities earlier that we can have on these devices. And here's an example of something called Ramsey coherence, T2 Ramsey of about 100 microseconds. But of course, we know that 1D chains aren't enough. We want 2D arrays. And so here's an example of a 2D circuit with 16 qubits that we're measuring in the group here at MIT. But you can already see that things are getting a little crowded. So to address all of this 16 qubits here, we need to bring control lines and readout lines in from the side, and you just run out of room. And so to access some of these in the middle, we have to bring in long wire bonds, and that's not good from a microwave perspective. And you can imagine that as we go to 5 by 5 and 6 by 6, that the situation gets worse and worse. And the point is, we know that laterally trying to wire these devices just isn't going to work. We have to break the plane, as they say, and move from 2 dimensions to 3 dimensions. I'd like to mention that we're in the process, due to a generous donation from Keysight Technologies, to building a 64 qubit capable quantum test bed. That's a refrigerator and the control electronics with enough wires that we can control up to 64 qubits. Now, we're not going to start there. We're going to start there with something like this, 16 or maybe 25 qubits. But this is really fantastic and enabling. We really thank Keysight for that generous donation. But what we need to do is 3D integrate our processors, and we're starting to do that today. And what it looks like is something like this. It's a 3 stack, as we call it. There's a qubit chip on top, what we call an interposer in the middle, and then a readout and interconnect layer on the bottom. And the features of this is that the interposer is using the same type of high resistivity silicon that we use for the qubit chip to get high performance or long coherence times. And by using that same material as our interposer, basically the qubit always sees high Q material, and it doesn't degrade its performance. The second thing that's interesting is because we basically use the same wafer for the interposer, we have another surface that we can put active elements on, like tunable couplers or even additional qubits. And another innovation is these through silicon vias, which are superconducting. I'll show a picture in a moment. And what that does is it routes signals from the readout and interconnect layer up to the qubit layer. Now, this readout and interconnect layer is a multi-wiring layer chip where you have multiple wiring layers, and you can think of a complicated highway system where some highways go over some, an overpass and an underpass. And that allows us to route signals from the edge of the chip here to where they need to be. And then when they're under the qubit we want to address, we bring them up through one of these TSVs. So we call this a 3 stack. So the chip on top is the qubit chip. You can imagine without the wire bonds, say a 16 qubit chip like this, face down on the interposer. The interposer itself has these through silicon vias, and these are about 200 microns long or deep, if you want to think that way, and 10 to 20 microns in diameter. So an aspect ratio of 10 or 20 to 1. And they're lined with titanium nitride, which is itself a superconductor, and it superconducts at around 2.5 or 3 Kelvin in this case. And then this readout and interconnect layer, you can see is multiple wiring layers. The M means metal, so metal 0, metal 1, all the way up through metal 7. And it also has vias that can route signals from metal 1 to metal 2 to metal 3 to metal 4 to metal 5, etc. So these are the overpasses, the underpasses, the on-ramps, the off-ramps, etc. So we can get the signals where they need to go. Now, this process also has Josephson junctions, it turns out. And we can use it for things like making traveling wave parametric amplifiers, which are useful for reading out the qubits with high fidelity. And so with that, let me just conclude. Thank you for your attention. I'd like to recognize my many colleagues here at the MIT campus in the Engineering Quantum Systems group, as well as colleagues at MIT's Lincoln Laboratory. We all work together in a one team model. Also like to recognize the many sponsors that make the work possible. And with that, thank you again for your attention.
So, thank you, Professor Will Oliver. We are looking at our Discord channel, and we will see if we have any questions.
Sounds good.
Thank you so much for the talk, Professor Oliver. We do have a few questions. First and foremost, we'd like to start off with a question from David from USA. The question is, how many different alpha and beta complex number values can be realized by different qubit technologies? There are potentially infinite alpha and beta of complex numbers.
Yeah, that's a great question. So, if you have n qubits, you basically have 2 to the n components in the superposition state. That would be the maximal, superposition state. And then each one of those would have a complex weighting coefficient. So there's 2 to the n of those weighting coefficients. And in fact, they can be complex. So you can also have both a real and an imaginary number associated with it. So 2 times that. Now, you're absolutely right that you can basically continuously or in an analog manner tune any one of those coefficients. In principle, you could do that. But for computation, we limit ourselves to certain points on the block sphere, ideally, in our universal set of gates. And in particular, for what are called Clifford gates, you're basically at plus minus x, plus minus y, plus minus z. And that's not enough for universal quantum computation. You also need what's called a non-Clifford gate to take you away from those points. But with just a small number of points like this, we can then effectively take what seems like an analog problem that's really hard to deal with and turn it into a digital problem through quantum error correction and measurement. Because remember, measurement is going to snap you to one of those zeros or ones if you're measuring along the z-axis, plus or minus x, plus or minus y. The next question might be, okay, well, how can you do that if you've got all this delicate quantum information and you make a measurement? Don't you just ruin that quantum information because you project it out? That's true if you're measuring the state of the qubit, but you could ask a different question. And in fact, if quantum error correction or quantum error detection relies on the fact that we ask a different question. And often the question that we ask is related to parity. So you could ask a question like, are qubits 1 and 2 in the same state, or are they in a different state, right? And through that, you can learn whether an error occurred or not, and you can even learn on which qubit occurred, but you never learned, was it a 0 or was it a 1? And so you can come back in, for example, and say, for a bit flip code, I learned that there was a bit flip on qubit 1. I know that if I go in and flip it, I'll correct that error, but I never learned whether it was a 0 that became a 1 or a 1 that became a 0. And so the quantum information is protected.
Awesome, thank you so much. We have another question from Taha, CQ Tech Algeria. What is your opinion about some scientists in Japan who recently claimed they successfully execute an operation with 2 neutral atom qubits in just 6.5 nanoseconds? And that would be 3 orders of magnitudes faster than what is shown on the presentation. And there's a reference Nature article, but we don't have time to open that up. So
yeah. So, like I said, that there are some improvements that have been made. That chart which I made was intended to do something, which is say, look, what are the fidelities that have been benchmarked and published, right, using standard benchmarking techniques that we all accept so that we can compare modalities against one another? What are those fidelities and what speed was the gate that they used to do it? So I'm not saying that, a gate couldn't be faster. Maybe somebody did demonstrate a really, really fast version of that gate. And if they also then measured the interleaved randomized benchmarking or the process fidelity, right, then I should update my chart, right? And as I said, that chart was from 2019. So lots happened since then. But there are many examples of people who said, hey, I did this demonstration, I got this really fast gate, but they didn't measure the fidelity. Or I got this fast gate, but the fidelity wasn't that good, right? I was able to make it faster, but at the expense of fidelity. So what I was looking to do there is look at what's the best fidelity that's been achieved so far in that modality and what speed did they use to do it, It's got to use the standard randomized benchmarking procedure or process tomography procedure, and it's got to be published in a journal.
Great. Thank you so much. We have another question from Henri J. Benelli from Minnesota, USA. In designing hybrid quantum circuits with multiple degrees of freedom, what is something to look out for or be careful in terms of interfacing two or more quantum systems that make it hybrid?
Oh, hybrid systems meaning two different technologies together? Is that the question?
I assume this is maybe like a classical, maybe like a hybrid quantum, like, you know, a hybrid classical interface.
Oh, hybrid, I see, classical quantum system. Okay. Yeah, so, you know, things that we need to figure out in doing that are, you know, how does the quantum computing node that, so basically in this concept, the classical computer is doing most of the computation, right? And then at some point, it gets to some point in the algorithm where it wants to poll a quantum computing node to get a quick answer back, right? And so we need to develop algorithms, hopefully commercializable algorithms that take advantage of that. And so I would say the #1 challenge there is just developing algorithms that can take advantage of this and provide some advantage over what classical computers can do on their own today. I also noted that in the chat, it said they thought it was hybrid quantum systems. So I'll just address that one as well. If you have two hybrid systems, like a trapped ion and a superconducting system, and you want to put those together, the thing to think about is the following. You know, usually the intuition is that, oh, ions have great coherence times, so they last a long time. Superconducting qubits are really fast. Why don't we put them together like, you know, chocolate and peanut butter? But the problem there is that usually the exchange of information from the superconducting to the trapped ion, that coupling often goes at the speed of the ion trap, which is slower, which is part of the reason it has a long coherence time, or it's you know, it's related to the fact that it has a long coherence time. And so you'll lose information or fidelity on the superconducting side while you're trying to pass information over to the trapped ion side. Now, if you could make that so much faster, right, then you should just use the ion traps as your quantum computer, because now they have a really long coherence time and they're really fast. So that builds an intuition for us that if you're going to make a hybrid system, you have to make sure that you can leverage the advantages of both hybrid systems at the same time. And it's not obvious to me how to do that in many cases.
Thank you. We have a question from Taha from Algeria. What is your opinion about the progress of topological quantum computing approach? And which companies/universities seem to have the most promising architecture?
Well, topological quantum computing is still very early on in its development. That's not to say people haven't been working on it for a long time. They certainly have been. But making topological qubits is really challenging. Of course, Microsoft probably leads in this area here. And they have, you know, this year they've had some presentations and press releases about having demonstrated what's called evidence of what's called a Majorana fermion, which is an ingredient in building a topologically protected qubit. It's not a qubit yet, but it's a step towards that. So topological qubits are still at a very, very early stage. I don't know that we've demonstrated in that sense a topological qubit. On the other hand, the concept of topology underlies, for example, the surface code and how we can basically achieve resilience through redundancy. So by adding lots of qubits into a large grid and, you know, operating them in aggregate according to a certain prescription, we can achieve error correction, right? And basically, it's an error correction protocol, but it is based on ideas out of topology. So there's topological qubits, people are working on that, but then there's using the concepts of topology to realize error correction and protection.
Thank you. I think we have a few more minutes left. We have one more, another question from Bennett Brown, QSTEAM, Ohio. As much as I appreciate the creativity and work that went into developing lacrosse metaphor, is there an equally useful metaphor from soccer, basketball, or something else more culturally relevant to more students?
I'm sorry, could you repeat the question, Ricky? I didn't quite catch the question.
Yeah, sorry about that. So the question is from Bennett Brown from QSTEAM, Ohio. As much as I appreciate the creativity and work that went into developing the lacrosse metaphor, are there equally useful metaphors from soccer or basketball or something else more culturally relevant to more students?
They appreciate, I still didn't catch it. The metaphor for what?
So there was a great lacrosse metaphor, and
Lacrosse
yeah,
metaphor. Yep.
yes, and where there you talked about the cradling and
Yep.
about air correction, and the question is asking if there are similar metaphors, perhaps using other culturally relevant sports such as soccer or basketball.
Yeah, there could be. There could be. I like the lacrosse one because it's quite, you know, you actually cradle as a 180-degree rotation basically of your wrist, which is similar to what we do with the pulses, which is a 180-degree rotation of the qubit. So in some sense, it makes a connection there. Also running across the ground, being bumpy environment. So I find many connections there, but I'm sure that you know, you could think about other sports and try to tie it in as well.
Great. I think we have maybe one or two more questions. What is your take on using photonics for fabricating qubits? This is Tariq Islam.
My take on photonic qubits?
Yes, or
Yeah.
fabricating.
Oh, for
using photonics to fabricate qubits.
Oh, photonics
Yes.
to fabricate qubits. Well, we do in fact use, or we can use lithography techniques, optical lithography techniques to pattern and make these qubits. We do it for the larger features. We tend to use e-beam lithography for the smaller features just because of the ease of using electron beam lithography. We can change our minds a lot and tweak the designs. But in fact, you know, transistors are very, very small. And with state-of-the-art optical lithography, the feature sizes can be tiny, the reproducibility fantastic. And, you know, so people can certainly use these photonics to fabricate qubits. If you meant by that using photonics as the qubit, that is also very interesting. There are a couple companies doing that. PsiQuantum, Xanadu are two examples. And there often it's using quantum states of light and then in some cases building up a cluster, what's called cluster state, and then based on measurements you collapse it down, and it's the combination of cluster state plus the measurements which implements the algorithm.
Fantastic. I think we have maybe one last question from Juliana in Italy. In your opinion, how long will it take to have a fault-tolerant quantum computer? Is a 7-qubit quantum code the preferred option at the moment, or there is some error code in sight that requires less qubits to build fault-tolerant devices?
Well, it's anybody's guess, right, as to when we're going to have a fault-tolerant quantum computer. You know, I often turn the question around and ask, you know, when did we have a classical computer? I don't know, right? You know, the point is that it evolves over time. And so, you know, the computers we had in the 1950s were very, you know, slow and weak compared to what we have today. But that technology evolved. And so for quantum computers, what we can say is we don't have fault-tolerant quantum computers today, but people are starting to develop and demonstrate quantum error correcting codes. And, you know, I would say within 10, 20 years, we're going to have demonstrations of fault-tolerant quantum computers. But I also expect that they're going to start small and maybe not as good. Then they're going to get bigger, bigger, and better over time.
Awesome. If everyone could give a virtual round of applause to Professor Oliver. Thank you so much for speaking. It was really wonderful to learn a little bit more about superconducting qubits, the research you do, as well as the research you will be doing with quantum dots as well. So thank you so much. And I hope if everyone could give a round of applause, that'd be great. Thank you.
Yep. Thank you very much for the invitation. I really enjoyed it. And please enjoy the rest of your hackathon.
Thank you. Up next, we